Right, thank you. Well, hi, everyone. And I'm going to talk about covariate balance. So when we do our studies, we adjust for confounding, whether it's OHDSI, where we do tens of thousands of variables, or a traditional study where you do 5 confounders that you believe might be confounders. We adjust. The most common way to adjust is using a propensity score. I don't have time during this short talk to explain propensity score analysis. I'm going to go straight into the topic. The question we have when we do such a thing is whether you balance on 5 covariates that are confounders or 50,000, how do you know it worked? And in OHDSI, we traditionally, and most researchers will use covariate balance. That is, you have 2 groups you're comparing, and we take every variable that you're balancing and see whether they are equal in the 2 groups. And we use standardized mean difference to judge that. Norman and Austin came up with a threshold that said, well, if you have a larger and larger database, you're going to detect smaller and smaller imbalance, which we don't care about. It's not going to cause a big problem. Let's pick a threshold like 0.1. So we say 60,000 variables or 5 variables, whatever it is. Are any of them greater than 0.1? If they are, it's imbalanced, and we don't think that the study may not be valid. The problem for today is sample size falls. You always fail your diagnostics. Why? Because by chance, something's going to exceed that 0.1 threshold. So here's the formula for it. Basically, it says as the sample size drops, say with a total sample size of 250 cases and just 5 covariates, so this should be easier. That is, if you do an outside of OHDSI study, you have a 90% chance of rejecting your study as being imbalanced just by chance alone, not because there's really confounding or instruments in there. So what should we do about that? And the idea is, well, instead of checking whether imbalance is greater than 0.1, let's check if it's statistically significantly greater than 0.1. That way, as sample size falls, we should have a higher and higher bar to pass to call it imbalanced. So in other words, when we check for statistical significance, instead of 0.1, it's effectively going to be a higher number than that, and we'll call fewer studies as imbalanced. And that won't hurt us. Why won't it hurt us? Because as the sample size drops, the confidence interval around our effect estimate grows, and a small amount of confounding hurts us less and less because our estimate is so imprecise. Having a little bit of confounding doesn't hurt. So the fact that the threshold rises as the sample size falls is not a problem. So I'm going to compare 3 things in a simulation first and then real world data. What happens if you do nothing, which is frankly what most studies do? I skipped a slide that said most people don't check anything. The second one is called nominal. So all means I'm including all studies. I don't reject anything. Nominal means I check whether you're nominally worse than 0.1. So that's what OHDSI does today. And then signif is where we check for statistically significance worse than 0.1. That's what we're suggesting today. That's our proposal. Now, remember, we do network studies, so we have things at the network level and the database level. So there's really 9 things we can do because it's 3 times 3. I can check at the network level, are we balanced? And I can check at the database level, are we imbalanced? Here's a key point for this talk. When I do a meta-analysis on my effect estimate, I can also do a meta-analysis on every one of those 60,000 variables and get a summary standardized mean difference. The metrics I'll use are type 1 error, which should be 0.05, and power, which I want to be 1. Here's the answer for databases. It's a busy slide, but I'll summarize it. So the first row tells me type 1 error because there's no true effect. The rest of the first column, the rest of the columns say power because there is a true effect. And if you see the first row, it says no diagnostics, that's all. You see on the left, it says poor type 1 error. So the problem if we do no diagnostics is we get poor type 1 error. How poor? 100%. So the worst you can possibly do is 100% because we're aiming for 5%. So it's basically a completely invalid study. Second row, if we do what OHDSI currently does today, look at the far right. It says poor power. How poor? We want around 100%. And what do we get? The worst possible, 0. So it just doesn't work. But our proposal, which is the third row, we get moderate type 1 error, not perfect, and good power, as good as we get if we do nothing. So the only thing that works with small sample size is looking for statistically significant standardized mean difference greater than 0.1. Now let's go to network studies. And so now there are 9 possibilities. We go at the network level and then we go at the database level. Let's take the first 3. The first row, poor type 1 error. The second row, poor power. The third row, poor type 1 error. Basically, you can't ignore balance at the network level. No one in the world does meta-analysis of their diagnostics. Not OHDSI, not anybody. What this slide says is, if you're going to do research and you're going to do a meta-analysis across many databases, you need to do a meta-analysis of diagnostics also, because not doing it on all 3 options don't work. If we do that meta-analysis, we find the first and third row work here, the first and third row work here. Summarizing it, here are the algorithms that work. I don't want to dwell on it because we're going to knock them out in another way. So now we use real-world data from OHDSI Legend hypertension study, and we look at all the possibilities. Again, going through quickly to save some time. Basically, the 4 rows that were possibly viable before, we see that in real-world data, if at the network level, we check nominally greater than 0.1, poor power, again, down to 0. Now, and then the nominal on signif, that's also poor power. The only thing that works is if we look for statistically significantly worse than 0.1 at the network level, and we do something at the database level. So what we're finding here, there are only 2 algorithms that really work. I'm going to get to which one wins in the long run in a moment. And now, if you look, some of my type 1 error is not 0.05, it's like 0.1. Shouldn't it be 0.05? Why am I accepting a rule that's not perfect? And the answer is because of the nature of the thing. As soon as you accept an Austin 0.1 threshold for SMD, nominal or statistically significant, it's possible to create a simulation that breaks it. Here's an example where I make the type 1 error 0.5. Even if I have 20,000 cases, a big study, only 20 covariates, I can still break it. The point is that we can correct for these moderate difference in type 1 error through our negative controls. If I drop it from thousands of covariates to the 20 covariates that other people do, I get the same results. If the confounding is heterogeneous between databases, I get the same results. If I have only 5 databases instead of 20 databases, that's where only one rule wins in the end, and that's doing statistically significant imbalance at the network level and statistically significant balance at the database level. So it's a 2-step process. You see if your databases pass the test, then you see if your network passes the test. You think I'm doing a Bonferroni correction on the statistical significance. Doesn't that raise the threshold really high? Well, in practice, we're finding it still works. And the reason we're doing this in the first place is because all those extra variables we include, some of them are confounders and we don't want to miss them. Then you can say, well, isn't this all a moot point? I have a study with only 250 cases. How can I even calculate a propensity score? Well, Martijn Schumi already showed that you can get a stable propensity score even at 250 and maybe 25. So, in conclusion, small cohorts, as your study size falls, this is not small databases, it's small cohorts. So it may be a large database, but it's a rarely given treatment or something that you're comparing to. Small cohorts, based on OHDSI's current method, have a 100% chance of rejecting the study and 0 power, and there's no sense in carrying out the study. As sample size falls, the confidence intervals get larger on the effect estimate, which gives us a benefit. That is, it can accept some extra confounding. So if we do this statistical test for imbalance, instead of just doing the nominal one, we actually get the best balance of type 1 error and power. If you do a meta-analysis of your effect estimate, you have to do a meta-analysis of your diagnostics also. That's a general concept. So that's shown here, which I demonstrated. Let's say you're not an OHDSI, you only check for 10 covariates that you think are confounders. You ignore the other 60,000 variables. An important point, using this method, even though you only adjusted for 10 variables, you should be checking all 60,000 for imbalance. And if any are imbalanced, you should be convincing us in your paper that they're not confounders, that they're instruments, or it's just chance or something else. You should not be able to get away with not checking for imbalance on every covariate you have. Not doing that is a head in the sand approach. I'm going to pick these confounders and ignore the others because I know they're going to come up negative because I know my study's invalid, but I'm going to publish it anyway. So check for imbalance, statistically significant imbalance greater than 0.1 in every covariate, in any covariate. And network studies require meta-analysis. And you need to check all covariates, not just the ones you happen to adjust for. Here's the team that worked on it. Thank you very much. The funding. And the paper is sitting on archive for a slower version of the talk. Thank you.